Thank you for joining me today as we explore one of the most intriguing new ideas in planetary science. We've always thought of the Moon as a close sibling of the Earth, tied to us not just by gravity but by origin. However, new research is challenging that assumption, suggesting that our Moon may have been adopted by Earth rather than being born alongside it. The Moon, as you know, holds a special place in our solar system. Unlike other planets, which have either multiple moons or none at all, Earth has this one prominent satellite. The Earth-Moon relationship is also distinctive for the unusual size ratio between the two, making our system unique in the solar system. So, how did this fascinating relationship come about? To understand the new theory, let's start by examining what scientists have believed until now. The giant impact hypothesis has long been the most accepted explanation for the Moon's origin. According to this theory, around 4.5 billion years ago, a Mars-sized protoplanet collided with the early Earth. The impact was so intense that it flung a huge amount of debris into space. Over time, these fragments coalesced into what we now know as the Moon. This theory is strongly supported by the fact that the Earth and Moon share a remarkably similar composition. In fact, their mineral and isotopic makeup is so close that it almost seems like they were formed from the same material. However, recent findings indicate that there could be another explanation that's equally compelling, if not more so. Let me introduce you to a new theory led by astronomers Darren Williams and Michael Zuger at Pennsylvania State University. They proposed that the Moon could be an adopted celestial body, captured by Earth's gravitational pull after it had already formed somewhere else in the solar system. This concept of gravitational capture is quite radical because it redefines our understanding of how planetary moons can come to be. Now, how does this capture theory work? The process is known as binary capture, where two celestial bodies initially orbit each other. If a third massive body, in this case, Earth, passes close enough, it can interfere with the gravitational relationship of the first two objects. The result, one of the objects is captured by the larger body, while the other one is sent off or destabilized. Intriguingly, we see hints of this process elsewhere in our solar system. Neptune's moon Triton, for example, is thought to have originated in the Kuiper belt and later got captured by Neptune. Triton's unusual retrograde orbit, which runs opposite to Neptune's other moons, suggests a foreign origin. Could something similar have happened with the Moon? Williams and Zuger's models suggest that Earth could, indeed, capture a body about the Moon's size under the right circumstances. A larger object, the size of Mercury or Mars, would be too massive for a stable orbit, but a Moon-sized object could settle into a gradually more circular orbit, similar to the Moon's current path around Earth. Additionally, their model explains why the Moon's orbit isn't perfectly aligned with Earth's equatorial plane, a characteristic we would expect if it had formed from a collision. But what about the Moon's strikingly similar mineral composition to Earth's? This is a question the capture theory faces, and scientists are actively exploring answers. One possibility is that both Earth and this foreign moon were formed from similar materials in nearby regions of the solar system. Or, alternatively, the Moon might have passed through a cloud of Earth's debris after it was captured, eventually absorbing some of the same material. There is also an intriguing concept known as synestia that could provide additional insight. Synestia refers to a hypothetical, rapidly rotating, donut-shaped mass of vaporized rock that forms after planetary collisions. It's possible that both Earth and the Moon coalesced from a single synestia structure, which might explain their shared material composition even if they originated separately. Now, why does this theory matter beyond the fascinating origin story of the Moon? Darren Williams emphasizes that understanding the Moon's origins isn't just about Earth's history, it's about our entire galaxy. If binary capture is possible, it could mean that other star systems have similar arrangements, with planets capturing foreign moons. This expands our understanding of where life-supporting planets and moons could exist beyond our solar system. Additionally, the Moon has played a crucial role in Earth's evolution. Its gravitational influence stabilizes our axial tilt, moderating the seasons and creating conditions favorable for life as we know it. If a captured moon could provide such stability to another planet, it opens up exciting possibilities for habitable worlds beyond Earth. Of course, like all theories, this one is still in its infancy. The giant impact hypothesis remains widely supported, especially given the mineral similarities between the Earth and the Moon. But what Williams and Zuger's work shows is that there are still open doors in our understanding of cosmic evolution, even within our own solar system. In conclusion, the idea of the Moon as an adopted, body, captured by Earth after forming elsewhere, invites us to reimagine the story of the Moon and its role in our planet's history. This new perspective also offers a fresh lens through which we might study other planetary systems and their potential for supporting life. Thank you for your attention. I hope this exploration has sparked your curiosity and perhaps even inspired you to look at the night sky a little differently, wondering if the Moon is indeed our sibling, or perhaps a long-lost friend we were lucky enough to find.